Hi, everyone. Today we're doing a lesson on probability with permutations. So we're going to revisit some problems we may have done before in terms of using probability and maybe look at them in a fresh way using organized counting and permutations. So let's dive in. In our first example, we're looking at a multiple choice test, and we have 10 questions and 4 answers, A, B, C, or D. And we're going to look for what the probability that all 10 questions have C as the correct answer. Sometimes professors or teachers might put them all C as just to kind of troll their students. Let's look at the probability this would happen by random chance. So let's try yellow for today. So method one, what we could do is we could use our probability knowledge. Each of these test questions are kind of independent of each other. And so I'm going to say we can use compound events, our knowledge from our probability unit. So the probability of 10 C's, I'll say, in a row. Well, let's think about the probability that the first question is going to be C. Well, there's 4 options, A, B, C, or D. And 1 in 4 chance that it's C. That's for Q1. And for Q2, there's also a 1 in 4 chance that it's C. And you might see where this is going, all the way up to a 1 in 4 chance for question 10. That one's part C. A quicker way to evaluate this would be to do 1 over 4 all to the power of 10. So we can do that. That would give us 1 over 4 to the power of 10 is a fairly large number. This is about a 1 in a million chance. So it could happen on some randomly generated test, but just over 1 in 1 million. So this is a question we've already explored. We have the skills to do so, to do this question. But let's look at how we can do this question using organized counting. So in method 2, we're going to look at the same problem a different way, and we're going to use organized counting. So remember that the theoretical probability of some event happening A, it's the number of ways A can happen divided by the number of elements in the sample space. So if we can use organized counting to find those two things, we can get the probability. So in this problem, the number of elements in the sample space, well, there are 10 questions, and there's 4 different ways that you can answer, or that the answer can be chosen for each. So for Q1, there's 4 options for the answer, A, B, C, or D. For Q2, there's 4. And you could set up an FCP calculation if you'd like, but hopefully you're kind of convinced that what you're going to get is, you get 4 options for each question. That's going to result in 4 to the power of 10. This is just using the fundamental counting principle. And we get that familiar number from our previous work, 1,048,576. The number of ways that we could have, 10 C's in a row be the answers for our test. Well, there's just one way that can happen. They're all C's. So the probability of getting 10 C's would just be this number of ways it can happen, one way, out of the number of elements in the sample space, 1,048,576. Same answer. Each method is equally valid, just 2 different ways of thinking about the same problem. Let's move on. In this question, we have 8 people on a waiting list. They're waiting for some advance tickets to a concert. They've been chosen to choose their seats. So we're going to find a probability that they're going to be notified in order from youngest to oldest. So we're going to start off. We're going to do this 2 ways again. And just like the last question, we're going to do it using compound events and probabilities. And then we're going to look at it using organized counting. So we're going to find the probability of the, I'll just say the correct order. And so let's think about it. So our first person is being chosen. Our first person is getting notified. What's the probability that they're going to be, it will be the youngest person? Well, they're of the 8 people on the waiting list, there's one that is the youngest person. So 1 out of 8. Now we'll move, I'll just say P1 for like person 1. Now on to person 2. These probabilities we're multiplying, these events are dependent of each other, because now we've already chosen one person. There's now one less for the next probability. We only have 7 people left for the next notification. And of those 7 people, one of them is the youngest of the remaining people. And then we can continue down the line. For person 3, there's 6 people left, and one of them is the youngest of those 6. And we're going to go down the line. I will write out, in this case, it's not too bad. 1 over 3 times 1 over 2. And then at the end, for the 8th person, there's one person that's left. So you can say 1 out of 1. And that gets us up to person 8. And we can just do this calculation. 1 times 1 times 1 is 8 times is just 1. In that bottom calculation, you might actually recognize as 8 factorial, or you could do the multiplication. Doesn't matter. But you get 40,320. So, if this were to happen about 40,000 times, only about once would you expect them to be notified in the correct order, youngest to oldest. So again, a problem that we could have handled in our previous unit. Let's look at it using organized counting. So let's do this a second way. So again, in this method 2, we're going to use organized counting. We're going to use our counting techniques to figure out, well, how many different ways can this happen? How many elements are in our sample space? So we're selecting 8 people, and we're selecting 8 people in a very specific order. We're arranging all 8 people to be notified. So at this point, we know that the number of ways to arrange 8 people, that's 8 factorial. And that's not surprising, because that calculation showed up in method 1. 8 factorial, 40,320. Of those 40,320 different orders of 8 people, the number of ways that they are in the right order, I think that's how I phrased it last method, there's just one correct order, right? So the probability that they are chosen in the right order, it's the number of ways they can be in the right order, 1, divided by the number of elements in the sample space, 40,320. So again, sometimes we can, a problem that we could have looked at using compound events in our probability unit, we could also think of interpret them using organized counting as well. Let's move on to example 3. So here we are going to do like just a card example here, the context of 5-card stud. 5-card stud is a very a simple game. You basically just dealt 5 cards from a deck of 52, and your hand is your hand. And from those 5 cards, you want to have the best hand possible. You want pairs and triples. You want them all to maybe a straight or all the same suit. That's called a flush. So we're going to use that game for these questions here. We're going to find the probability that a player playing 5-card stud is dealt 4 kings and then an ace. So we're going to do this problem using permutations and organized counting. So the first thing we need to do, it's a probability question. We need to figure out, well, how many elements are in my sample space here? How many different hands could Johnny get? Well, the number of ways to deal out 5 cards, and this isn't a specific order. Maybe you might be thinking, well, does it really matter what order the cards come? In a game like Stud, it actually does, because you actually turn up the cards as you're dealt them and kind of bluff your way, and there's rounds of betting. But if you're playing a game of euchre or Go Fish, or a normal card game, usually you get your hand of cards, and it doesn't matter what order they're in. So we are implying a certain order here. Of the 52 cards in a deck, we're arranging 5 for a hand in a specific order. So that's 52 P5. That's a fairly large number, but not so large we can't evaluate it. 52 P5 is 311,875,200. So this is the number of different possible orders of hands, 5-card hands you could get. Again, implying order matters. So now let's think about, well, how many ways could Johnny get, I'll say 4 kings, and then an ace. I'll just write it like that. We got to use our skills from our previous day where we combine methods. So let's think about the number of ways that he could be dealt his 4 kings, and then talk about the number of ways he could get his ace. So order matters here, and the number of ways that the 4 kings could be dealt out is, well, all 4 kings, and we can arrange those in any different way. That would be 4 factorial. There's 4 factorial ways for those 4 kings to come out. It could be like hearts first, and then diamonds, and then the king of spades, and then the king of clubs, or it could be, hearts first, diamonds first, and hearts second. The number of ways to arrange those 4 kings would be 4 factorial. And then after that, the number of ways for him to get an ace, well, there's 4 aces in the deck, so times 4. So this is a little fundamental counting principle combined with some factorials. 4 factorial is 24. 24 times 4 is 96. There's 96 ways this can happen. So the probability of getting 4 kings and then an ace is pretty rare. This would happen 96 times out of 311,875,200 hands. And for this question here, we can leave that as it is. There's not much value in simplifying that or making it a decimal. We just want to illustrate the process here. So having done that one, why don't you try and use the same logic for this question? So keep in mind, in this question, we have it's the same sample space. We're still playing 5-card stud, and the number of ways to have that. You guys will have that down in your sheet. I'm just going to get it on my slide here so I don't have to keep flipping back and forth. So your probability initially will be out of 311,875,200. But maybe you want to take a moment and see if you can figure this out. How many ways can you get 3 10s, then 2 queens? Set up a little calculation here. So if you want to pause the video and figure that out, you can unpause it when you're ready. Or if you'd like to just follow along now, you can. So how many ways can we get our 3 10s? Well, so now we're not arranging all the 10s, right? Johnny is not getting dealt all the 10s. He's only getting 3 of the 4. We know the number of ways to arrange 3 10s from the 4 would be 4p3. The number of ways to get 2 queens, again, he's not getting all the queens. He's just getting 2 of them, would be 4p2. 4p3 ways to get the 3 10s, and then 4p2 ways to get the 2 queens. Do this calculation. Times 4p2. 288 ways that this can happen. So the probability of this particular hand, so a full house in this specific order, 3 10s, then 2 queens, 288,000 out of 311,875,200. And we'll just leave it at that. Again, we could put that in lowest terms. Not a ton of value in doing that. But if you'd like to, you can for sure. I may actually just revisit the previous question. When we had 4 ways to select one ace, we could have also thought of that as, of our 4 aces, we're just selecting one of them, and you can verify for yourself that 4P1 is indeed 4. Also, we touched on this last lesson, but 4 factorial, another way to think of that was of our 4 kings, we're selecting and arranging all 4. And you can check that 4P4 does give you the same thing as 4 factorial. All right, so we've did some questions, tied in our organized counting in order to find the number of ways an event can happen and elements in the sample space. We can actually use organized counting to revisit our birthday problem. If you recall, our birthday problem calculations for a large group of people could be very, very cumbersome. You might have been multiplying. So if we're looking at a class of 28, the calculation for the birthday problem involved like 28 multiplications, 27 or 28. And that's a lot. But we can actually, when we set up this problem, we're going to see that we can use some of our new knowledge to make this problem even simpler. So if you recall, our strategy for finding, the probability that 2 students share a birthday was to use the indirect method. And we looked at the probability of having no shared birthday first. And we talked about this in one of our first few lessons. But so for our first person, we asked person number 1 in the class, what's your birthday? They have all 365 days available to them. However, when the second person is asked, to make sure that they don't share a birthday, they only have 364 days to choose from of the 365. So there's a 364 and 365 chance they won't match. For the third person, there's now a 363 out of 365 chance that their birthdays won't match because 2 days have been used up. And we do this for all 28 students in the classroom. So if you count down from 365 and include 28 numbers, that gets you down to 338. As of several lessons ago, we would be stuck actually having to do that big multiplication, which is kind of cumbersome. But actually now we have a quick way of doing that. The bottom is just 365 to the power of 28. But the top is the very definition of 365 P28. Right? 28 slots, 365, 364, counting down 28 times. And so now we can actually do this calculation very quickly and easily on our calculators. We can't do 365 P28. Well, maybe we can. It might be too big to put in your calculator and display it nicely, but you can just do that all at once. 365 P28 divided by 365 to the power of 28. And you're going to get I'll go to 4 decimal places for my decimal, or that's 34.55%. So remember, that's the probability that no people share a birthday. So either nobody shares a birthday or at least 2 people share a birthday, like maybe even more. But the probability of a shared birthday would be 1 minus 0.3455. Which would be somewhere around 65%, 0.6545, or 65.45%. So that's interesting. In a class of 28, it's almost 2/3 chance 2 people will share a birthday. So I thought it would be good to revisit the birthday problem because we can now think about it in terms of organized counting and permutations. I'm going to switch colors here just to illustrate something. Maybe I'll try this bright purple. So if we were to redo this question, and let's say you want to do it for a class of 30, well, you wouldn't have to keep resetting this up. You would just do the probability of 2 people not sharing a birthday would be 365P30. You just now do 30 people and do 365 to the power of 30. And if you want to do a class of 30, 35, 365p35. And you just do this process, 365 to the power of 35. So it's really easy to set up the birthday problem now that we know about permutations. The last thing for you guys to try is how large does the group have to be until there is a 95% chance that two people share a birthday? So obviously it's more than 28. But why don't you try, maybe try 30, try 35, see if you can figure that out. Maybe pause the video. To maybe give you a little shortcut here, I'll keep my purple pen. This means that there's a 5% chance of no shared birthday. So you can just try some of those calculations we just talked about and see when you get to about 5%. And that means the probability of having a shared birthday is 95. You can pause the video now if you'd like and unpause it when you're ready. And I'll just try a few calculations myself and see what we get. So here we go. So I'm going to look at what 365p. I'm going to try 35 first. 365 to the power of 35. So I'm looking to get 5% because that means there'll be a 95% chance that two people do share a birthday. If you were so inclined and you had the talent, you could write a computer program that tests these out for you. So I got 0.1856, or you could put these formulas into a spreadsheet. So that was too low. What about a class of 40? Really big, not unheard of. Hopefully none of you guys are in a class with 40 people. But, if you go on to your post-secondary education, you'll definitely have classes that are, they're more like lectures, but be a lot of people. So 365 P40 divided by 365 P or to the power of 40. All right, so actually, this number is actually too big to handle on my calculator. It's too big. So I think we'll actually just call an audible and say just stop there. That might be something for you to look up online. I might dig myself and try to find a computational tool that allows you to handle these bigger numbers. The problem is that 365, if you try 365 P40, what you get is a number. If you do this on your calculator, you get an error message, at least on a standard one. That's because it's too big to store on your calculator. So let's actually just call an audible and let's stop there. If that's something you can investigate on your own, just for general interest. I do believe it's around 45 people that it gets to 95% chance, but you can look that up. I would like you guys to be able to do the birthday problem now. It was a bonus on your unit test, but at this point, with our knowledge of permutations, you guys should be able to handle a question like a class of 28. All right, guys, so that concludes our lesson on tying in organized counting and permutations to probability. I hope you guys have a great day, and we'll see you online.